Ahmed, should we go ahead and start? I just read your message. All right, fantastic. So thank you very much. I'll make a quick introduction. Thank you for joining us for the reinvent recap. This is positioned mainly for the Riyadh user group. And I'd like to say thank you to you as well, Ahmed Samir, for putting this together, and especially given the constraints that we've had. I appreciate very much you pulling this together around all of those challenges. We'll try to make it as worthwhile as possible for everybody joining the call today. Just as a sound check, I'm looking towards Paul Maddox. Yep, we have good audio. Thank you very much. So by way of quick introduction, my name is Anver Vanker. I am a solutions architect manager working for AWS here in Dubai. I've been at the company now for just over 2 years. I'll be joined by another speaker tonight by the name of Paul Maddox. He'll have a chance later on to introduce himself more properly. In terms of the agenda, we will spend the next 2.5 hours going through a summary of networking and security. I will hand it over in the next hour and a half, or just less than the next hour and a bit, to Paul, who will then take us through storage, compute, container, and serverless updates. We will take a small break around 15 minutes between our respective sessions, and that will take us to the end for the evening and line us up for tomorrow night, where we will pick up new topics being big data and analytics and AI ML. Your speakers for tomorrow would be Asif Abbasi, who's a specialist SA, and of course Ahmed Rafat, who I believe many of you are familiar with. And he will cover off AI and ML. As we get started, if I could make one request, if there are any questions, to please post them in the Q&A window. That would be the WebEx Q&A window. We will have some additional AWS SAs looking into that window to, to try and answer any questions that you may have. It's quite a large audience that we're expecting, so it will be a little bit difficult to open the bridge up to verbal questions. So if we can do it that way in terms of using the Q&A window, that would be greatly appreciated. So I'm going to go ahead and jump straight into it. Again, I'll be covering off networking and security, and I will start off with networking. And since this is a recap, I'll start the evening maybe just recapping some basic AWS networking capabilities. We always start off from a region perspective, and very simply, a region is a physical or geographic area where AWS has infrastructure that we offer services from. That in turn breaks down to multiple availability zones, very similar to the one that you see on the right of the screen right now, which is the US East 1 availability zone. Typically speaking, an availability zone is made up of 3 AZs, as they are also affectionately known. Just to keep the drawing simple, I only have 2 to the right-hand side right now. In turn, each availability zone is, of course, made up of racks and hosts. That would be hosts or compute hosts, networking switches, routers, and of course, storage. And it is on that infrastructure across which we run all of our services. We then introduce within that whole concept the idea of a VPC, or a virtual private cloud. A virtual private cloud simply is a logical construct, if you like, that partitions, logically speaking, within the AWS region, those instances or those resources that you wish to launch. So basically within a VPC, you have the capability to, again, launch different services like compute instances. And you also have the ability to configure and run your own or unique IP addressing, or even public IP addressing. So we can go a little bit further with that whole concept, again, within a VPC. In this instance, in the US East region, I show a VPC that is made up of multiple instances, and at the same time also has public subnets associated with it and private subnets. Important to note is that subnets never stretch between availability zones and are always housed or contained within their respective availability zones. Now, a VPC also has the ability to have different types of gateways associated with it. So you'll see to the top of the screen, the little purple bubble is an internet gateway. To the right of the screen, we also have a VPC endpoint. To the lower half of the screen, we have another purple little bubble, which is an IPsec or a VPN gateway. And to the left, you'll see the concept of a peering gateway, which we'll get to a lot more as we go through the slides in the coming minutes. Within each of the availability zones, of course, we have EC2 instances that I mentioned about, but all of the various AWS services can be launched from within the VPCs. And you'll see one other example of that being a load balancer, which is the little purple circle that you see associated with the public subnet right next to the instance. So these are just ideas or constructs of the different services that can or may be associated with the different availability zones, and again, tied to a VPC. So how do we go about connecting VPCs to each other? And if we can start by looking at this very simple example, again, we have 3 VPCs, and as we mentioned earlier on, we have the ability to define subnets within a VPC. This is one of the benefits of defining or building your own VPC. You see a subnet, for example, to the top left being 10.0.0.0/16, which is, so we've just got some feedback. There we go. Which is considered a Class B subnet. We have another VPC to the bottom of the screen, 172.31.0.0, and to the top right, again, another VPC, 192.168.0.0. So these are all within some kind of a region, and very simply, we can connect them via internet gateways that attach to each of the VPCs, and the connectivity may be provided via the external internet. This is the most simple way, if you like, of connecting VPCs to each other. And in this particular model, it uses, once again, the external internet to carry that traffic in and amongst the VPCs. Now, we also have a more sophisticated capability, if you like, which is what we call VPC peering. Once again, within the same region, you have the ability to link these VPCs together, but using instead the AWS backbone. So instead of going out into the internet, you have high-speed connectivity within a region. Why not make use of that? After all, it does give a lot more predictable performance, and it is, of course, a lot more secure as well. So VPC peering is a capability that we use to deliver that with. The way you go about configuring that is through the AWS console. This is just one of the boxes, one of the configuration elements that would be used to complete that configuration. What you would need to supply to do that with is to firstly select a local VPC to peer with, right? So you would make a request to the remote end. There would also be an acceptor. So once you have configured this particular dialog box, you would have to go to the destination VPC and accept this configuration as well. And you can see from this box, it is very clear in terms of the CIDR ranges or the subnet ranges that are associated with each of the VPCs that we will be building this between. Once we've got that all configured, we have a peering in place. We then have routing tables that would also appear within each of the VPCs, allowing us to forward traffic between those VPCs. And again, this all happens over the internal AWS backbone infrastructure, and traffic never needs to leave to go out via the internet. Here you have an example of the routing tables that you see associated with each of the VPCs. So if we take the VPC at the top, there would be a local route, which is 10.0.0.0/16, being a locally connected subnet, with reachability to the 172.31/16 subnet via a next hop being the PCX or the peering connection. Similarly, at the lower VPC, there would be, once again, a routing table that has a local reachability of the directly connected network, 172.31, and reachability to the remote VPC, once again via the peering network. We can, of course, make this bigger. So most customers, or many customers, shall I rather say, have more than one, more than two. Sometimes it goes into tens, hundreds, even thousands of VPCs. So we can make this a lot more reflective of that by adding in this particular instance, a third VPC construct. And there you have its own subnet, 192.168, which is a /16, and a class B subnet once again. Important to note is that each of the VPCs in this instance have unique IP address space. So we have no capability at this point in time for the purposes of this example to offer overlapping IP address space. Okay. If we were to go through the routing tables in this instance, it gets a little larger, obviously to accommodate now for the third network that we see from the third VPC. And the same will be reflected in each of the VPCs that have reachability for locally connected subnets and, of course, remote subnets as well via the peering link. That's all fantastic. The question then becomes, what happens if I do not have a peering link between, let's say, the two VPCs to the right of our little triangle? Is it possible in that instance that traffic can go via a transit VPC, being the apex, in this case 10.0.0.0 VPC? And the answer would be no. By default, this is not supported. You would need to do a transit VPC configuration via the third VPC in the middle to support this type of configuration. And this is a good point to bring in the concept of the AWS Transit Gateway. This is something that was introduced a while ago. I think it was 2 reinvents ago, so going back to around 2018. It still makes use, once again, of the internal backbone infrastructure, the AWS internal backbone infrastructure. But what it does is the following. So imagine for a moment that we introduce 3 more or 2 more VPCs in this example. We need to then have peering between each VPC and every other VPC. So it becomes quite complex in terms of lots of configuration that needs to be completed. And furthermore, every time we introduce a new subnet, there's additional configuration that needs to happen within each of those VPC or peering configurations. So it becomes a lot more cumbersome to maintain something like this. And of course, it lends to potentially a lot more security issues because there's so much more that needs to be considered. So the Transit Gateway effectively solves this problem very, very simply by configuring, firstly, a transit gateway that all of the VPCs that you see in the drawing would attach to. So instead of, once again, having individual peering configurations between every other VPC, we have a single transit gateway that encompasses all of the configuration, in a single place. So here's a little bit more of a practical example. We have 4 VPCs. We have a corporate data center that also has some kind of connectivity that we need to use to reach our VPCs. The transit gateway would have VPC attachments, individual VPC attachments to each of my 4 VPCs. And in the case of the corporate data center, I have a VPC or a VPN, attachment that goes backwards and forwards between the transit gateway and my on-premises data center. Of course, the same topology could equally apply to a direct connect model as well. But just for the purposes of this example, I've decided to show a VPN attachment using an IPsec gateway. Now, in this example, we can have traffic traversing VPC to VPC via, once again, the transit gateway. I could also have traffic leaving the corporate data center that is destined to either or any of these VPCs via the VPN attachment. Important also to highlight the way our routing table would look in this particular example. So if we take the lower VPC, I would have routes in there to reach the 172.16 network via the transit gateway. The 172.16 network belongs in the corporate data center. Traffic then destined to that network would make its way via the transit gateway. Within the transit gateway, there would be another routing table that would again point us to the location or the next hop to reach the corporate data center. So in summary, Transit Gateway is a construct, is a method or a service rather that allows us to have multiple VPCs. It can scale to thousands of VPCs within the same region. It, at the same time, also allows VPN connectivity and direct connect gateway connectivity from on-premise data centers into the AWS cloud. Important to also point out that it works amongst AWS accounts, so it is absolutely multi-account capable, and as I've already mentioned, can interconnect on-premises networks as well. So coming forward to reinvent, this was the first announcement that I'd like to highlight, which is the availability of Transit Gateway for inter-region peering. So in as much as we've spoken about Transit Gateway within a region, we have the ability now to implement the Transit Gateway function between multiple regions across the 22 regions that we have worldwide today. The benefit of doing that is that we can easily share resources among and between regions. Of course, we also have the ability to encrypt inter-region traffic with no single point of failure, as you see in the notes. And we can scale this once again in terms of creating a hub for thousands of VPN connections and direct connect connections anywhere across the globe today. What it actually looks like is a full mesh of connectivity if we were to scale this out to multiple regions, as you see right now. Today, there is no dynamic routing protocol that we have available with this particular model. This is something we're working on. So it is static peering today. All traffic would go across the Transit Gateway peering connection being encrypted at the same time. And finally, it is horizontally scalable. So anytime we need to bring in more of these transit gateways, we can easily do that without much fuss. So for the next service that I'd like to introduce, as I get into that, it's important that I position something called the Global Accelerator. This is actually a service or a capability that we introduced last year at reInvent, and it goes something like this. Imagine we have a service running for a customer out of US East 1. That could be some kind of a web front end. And that web front end may be accessed by a community of users somewhere in North America. They are accessing that service via the internet. Of course, because it is connected to the internet, we can have users accessing that service from just about anywhere in the world today. Once again, that will happen via the internet. The challenge with this type of model is that depending on where you're situated across the world, you would be exposed to this concept of internet weather. And to double click a little bit more on what I mean by that, let's look at a more simplified example. So we have a user that's located probably across some kind of a Wi-Fi network, either in a corporate office or maybe even at home, accessing to the right-hand side some kind of AWS service. Behind this Wi-Fi router would be a local ISP, and behind the local ISP are a series of different other ISP networks, as you see listed as A to F. Traffic leaving that particular user destined to AWS would of course take a routing or a forwarding path across different networks, which could be very well different for the path that is, or the reverse path taken back from AWS to that user. The resulting experience of that user could be a number of different hops with different jitter and different latency that is associated with that. So the experience wouldn't necessarily be consistent with that in mind. What we're trying to do with the Global Accelerator is to really allow traffic from that particular user to enter the AWS Global Backbone Network at the closest point of presence, or from the closest point of presence. And we do that by making available the concept or the idea of an anycast IP address for the service that the user is trying to reach. So the local ISP would effectively route that traffic to the closest AWS point of presence. And from that point onwards, it is traversing the AWS Global Backbone, which is a low latency backbone and of course a secure backbone that effectively circumvents all of the issues that we saw on the previous slide related to this concept of poor internet weather. Just to give you a visual of what the AWS Global Backbone looks like, it is made up of a number of redundant 100 gigabit per second Ethernet connections that effectively traverse the globe. From a region perspective, we have our own region here in Bahrain. We also have POP locations in Dubai and Fujairah, and of course Bahrain, which are the closest points of presence to the AWS network. So taking that closer to the next announcement that I'd like to make, or to expose to you rather, is the idea of a AWS accelerated site-to-site VPN that effectively is built on top of the global accelerator. So today, trying to build any secure site-to-site VPN connectivity from a branch office, from a corporate office into AWS would effectively mean using a destination VPN IP address that could take you over multiple different ISP paths. With the accelerated site-to-site VPN, you have an anycast VPN IP address that would route your traffic to the closest AWS point of presence, and once again circumventing all of that internet weather that we saw about earlier on. The end result, or the net result, is a much more improved performance of your VPN connections using this type of capability. Next little announcement that we saw was something that we called the AWS Gateway Network Manager. The Gateway Network Manager is basically a capability that we have today to visualize any of this connectivity that I've just mentioned about. It is also the ability to bring in a very visual type of basis, health checks, the various KPIs like packets in, packets out, packets dropped across the network. And it also allows you to introduce the concept of SD-WAN using any of our partners that we have today on the marketplace into the Transit Gateway network. We have the ability to also manage this and build additional configuration using the network manager. And it is just a lot more easier to do this using a graphic interface as opposed to the usual console method that we have, which of course makes more sense when configuring networks. I'm just going to take a pause for a moment, glance over to Paul. Do we have any questions that I should be addressing for the moment, Paul? No. Cool. Thanks very much. All righty. So the next capability is Transit Gateway Multicast. So there are a number of applications today, specifically in the FSI world, that do make use of multicast capability. We haven't necessarily been able to support that in the past without the use of expensive hardware that we've had to build into a solution. From the 3rd of December last year, we effectively take that capability a lot further by introducing the Transit Gateway Multicast service. So dig a little bit deeper into that. Every time we provision a transit gateway, once again, you see the routing table that is present in a transit gateway wherever we make one available. In this particular example, we have a pair of VPCs, A and B, each with a subnet that is represented within the routing table inside of the transit gateway. We have applications in this particular instance that need to use multicasting, and through the various clustering techniques they have, the traffic uses multicast protocols to communicate amongst the cluster members. What we do in this particular instance is to create a multicast domain. You see the first of those in the little red bubble in the center of the transit gateway. We can build, of course, multiple multicast domains in this instance. Each multicast domains would have various multicast groups associated with it. An example of a multicast group IP address could be 224.0.0.5. For those of you familiar with OSPF, that is the SPF multicast address. But in essence, what we do is we create groups of multicast IP addresses. Within each of those groups, we have senders and we have receivers. we do need to denote or configure who the senders and who the receivers are. Today, there is no support for IGP. It is something that we're working on. Once that becomes available, of course, it becomes a lot more easier to join those multicast groups on a more dynamic basis. What it then effectively leaves us with is a sender can send out a multicast packet, and all the receivers associated with that group would dynamically receive that particular multicast packet based on the configuration that we've completed for the domain and the respective groups. Just to finish up on, or rather circle out this particular slide, today multicast is in use with a number of different clustering applications. I believe Oracle RAC is one of them. There are a number of databases that are also dependent on having multicast capability down at the network level. The next function that we introduced at reinvent is something called Ingress Routing, or rather VPC Ingress Routing. So for those of you who are familiar with building on-premises data center networks, this is something that happens quite often in terms of introducing services like firewalls, intrusion detection systems, IPS systems, and sometimes even load balancers by inserting those services inline to traffic entering the data center or inline to traffic egressing the data center. We've never been able to do that in an eloquent fashion, if you like, as it applies to AWS services. We now have the ability to do exactly that through VPC Ingress Routing. And through any of our partners today, well, actually those are limited to a few of them via the marketplace. Cisco, Citrix, and a few others have the ability to introduce their service appliances on an inline basis to traffic entering or ingressing a VPC, and similarly, to traffic egressing a VPC. So you could have, once again, as we've seen it on-premises data centers, a firewall that is inline that essentially inspects traffic coming into a VPC, and similarly, because of the stateful nature, would ensure that traffic egresses that VPC as well. The next service that I'd like to introduce is something called CloudTrail Insights, It's a pretty interesting service. In fact, I just had a chat about this earlier on today with some of the specialist SAs here in Dubai. What this essentially does is it takes a baseline of the type of activity that is happening within the environment. That could be activity like instances being terminated or maybe new EC2 instances that have been instantiated. And it takes a look at any deviation from that kind of baseline and would generate alerts for you the moment it detects any of that deviation. Pretty interesting from a security perspective as well, because obviously the challenge that you would have the larger your installation becomes is the more logs that you would have to sift through effectively to look for this information. This effectively automates this for you using some of the AI technology that we have behind the curtains. Amazon Detective, also something that we have within the security arena. This is also something of interest from the perspective that what it's really doing is consuming a lot of different telemetry that we have from various AWS services. Things like guard duty, things like VPC flow logs and VPC. Detective has the ability to ingest all of that information and to effectively visualize a lot of the flow of traffic as it passes through the AWS network. Now, where it becomes quite powerful is in the event of a security incident where you're really trying to get to the root cause of some kind of security finding. It has the ability to visualize, as I started mentioning a few moments ago, suspicious activity and really helps security administrators get to the bottom of those types of incidents. Moving forward to the IAM Access Analyzer. So it effectively ensures that anytime we create resource policies, so for example, resource policies that may be on an S3 bucket, as we change those policies, it ensures that we are not allowing any undue access, specifically as the environment grows and the number of accounts that we have available inside of the environment, it becomes a lot more complex, or could become a lot more complex to ensure consistency of the policies that we have in the environment. Access Analyzer is a way of working around that in a more automated fashion. And as I say, if we do have a situation where we are changing policies, it can automate the ability to see any new holes or any access issues that may be arising as a result of that. Finally, something that we've been doing for a while right now from a single sign-on perspective, this isn't necessarily something new. What we have brought to the market, and this was actually predating reinvent, going back to November 25th of last year, is support for Azure AD and as far as single sign-on is concerned. Single sign-on, of course, gives you the ability to choose an identity source. It is something that we've been doing a while for Microsoft AD. Office 365 has also played in there. We're really taking that a step further now by federating identity also into Azure AD. Cool. So moving on to a topic that is of interest to a number of us. We've certainly been having a lot of discussion around this in Dubai, is the topic of outposts. It isn't necessarily something new. It was actually announced back in reInvent 2018. It became generally available as of the last reInvent. So let me try and position this as we get into this in a lot more detail. Outposts is effectively a converged stack that AWS offers. It is composed of compute, networking, and storage. It is something that we pre-assemble and would ship out to a customer on order. It is based on exactly the same physical infrastructure that we use inside of our AWS regions. So it is the same EC2, it is the same EBS, and it is the same networking that we have within a region that is now packed into a rack that can arrive on order once again at your data center. It is built on what we call the AWS Nitro system, and we'll get into some of the details around the compute or the EC2 instance types that are available in there. It is a fully managed and monitored system that is operated by AWS. So all of the systems, all of the backend systems that we use to monitor our regions is exactly the same capability that we have that ships with Outposts. It is managed from the same AWS console that you would use for any of your AWS services today. So in effect, a single pane of management using once again the same APIs and tools that you would find inside of an AWS region today. Now, what is of interest to this from a customer perspective is that what we found is that a lot of our customers are looking for the same experience that they've had within an AWS region to be extended, of course, into their own data centers. So they're looking for the same reliability, security, and of course, high performance that they have come to experience and expect of an AWS region today. The same operational consistency. So everything that you would do today within the AWS console in terms of, for example, instantiating a new EC2 instance, standing up a new, for example, RDS database, customers want to see the same sort of capability on premises within their data centers as well. They want to do that via the same APIs, and they're looking for, once again, the same tools and automation to achieve that with. From an application perspective, why would you want to consider Outposts today? So one of the key drivers for Outposts is specifically in the area of applications that have a low latency requirement. and we haven't necessarily been able to keep up with that sort of low latency by having those applications live up within an AWS region. So this immediately solves that problem by having your application run on an Outposts rack that is physically installed within your data center. It offers near real-time application responses to your user applications. And the typical use case for this, for example, is in heavy machinery type of customers that need to control on-site equipment from their data center or from control within their data center. Another use case, typical use case for this type of infrastructure is for applications that need to process data locally. Good use case for this would be in a broadcast environment for live events where the data that is being fed in from cameras needs to be processed locally before being broadcasted out into the internet or more terrestrial forms of networks. These are the typical use cases that we have Outposts positioned for today. Now, what does it physically look like? And this is what would arrive on a customer premises after ordering an Outpost. In its basic form, it is a 42 RU rack. As I said, that is composed of networking, storage, and compute. It arrives fully assembled. So all a customer needs to do is effectively power this up and connect it into their network via either dual redundant 1 gig or 10 gig Ethernet connections. It will be installed by an AWS team. So there would be AWS engineers that would do a pre-site inspection to ensure the availability of suitable power and of course networking. The Outposts does connect back to a region of your choice. And one of the things those inspection engineers will do is also ensure that a latency not exceeding 150 milliseconds is in place between your local data center and the region that you wish to anchor this Outpost back to. It also has a centralized data center power conversion unit in it. So while we take in AC power, it is inverted or rather rectified down to DC, direct current. Everything in here is fed by DC. All components that we have in the system are dual redundant. As an example of that, you will see within this cabinet towards the middle a pair of Ethernet switches. They are both redundant, so if we lose one of those Ethernet switches, we will of course receive all of the necessary alarms within AWS, and we will have service personnel swap out the faulty switch within a period of 2 days. The same goes for many of the other components within the system. There's a ton of redundancy that gets built into an AWS Outpost rack. In terms of support, for Outposts, today there is a list of countries for which we support Outposts. Within our region specifically, it is available today for Bahrain, which means that you would effectively order an Outpost rack from the console. It can only be delivered to Bahrain today. We are considering extending that to the UAE and Saudi Arabia. We don't have any real dates for that as of right now. Expect to see further messaging for Outpost availability in the Middle East, specifically the UAE and Saudi Arabia, to the second half of this year. As I mentioned, an Outpost would anchor back to a region, and these are the supported regions for Outposts today. So once again, as an example, should a customer in Bahrain decide to order an Outpost rack, it would arrive in their data center, and it would anchor back to potentially the Bahrain region, which is denoted ME South 1, as you see it in the map right now. Now, Outpost is available in 2 variants. There is the native AWS variant. This would perform exactly as, or rather maybe configured exactly as you would configure any other AWS service today via the AWS console. which means it has exactly the same APIs. It has similar features. In terms of the supported services that we have today on the native AWS flavor of this, we support EC2 and EBS, of course. From a services perspective, that extends to RDS, ECS, EKS, EMR, ALB, and others that will follow in future. So this is the first flavor we have. The second flavor that we'll be shipping as well is a VMware variant of that. So for customers that have, or rather who have invested in an SDDC or software-defined data center that they're running on premises, all of the APIs and services and capabilities that come with that are capable of running on Outposts in this particular second flavor. They are mutually exclusive, so you would order either a native AWS flavor or a VMware flavor with that in mind. I've alluded to this a few slides ago, but maybe just to summarize in terms of the services that are available today on Outposts, you have them here on the screen. What we also do expect to come in the second half of this year, or later this year rather, is an S3 capability that will also be running on Outposts. Right, so in terms of the EC2 instance types that are capable of running on Outposts, you have them once again on the screen. So those range from M5 to C5, R5, G4 instance types, and of course I3. From an EBS perspective, this would be supported today on GP2 type volumes for both temporary and persistent storage. In terms of the catalog available on the console, we've pre-validated certain instance types that you see listed here. And again, you can test this for yourself by changing to the Bahrain region, just to get an idea of what are the catalog of EC2 and EBS types that can ship with Outposts. We do allow for some sort of tailor or customization of this. So while these we expect to be some of the more relevant flavors that we expect customers to be requesting, they will be, of course, tailored flavors that we're willing to make provision for and exceptions of that we will entertain as customers decide to order Outposts. Right, so what are some of the prerequisites that we have? Of course, we need to have a standard data center space. There you see in the slide as well the exact clearance that we need for that from a floor tile perspective. And from a power perspective, it's a minimum of 5 kVA or 5 kilovolt amps. From a networking perspective, we require either direct connect with the public VIF or a very simple internet connection via an ISP. So it does not necessarily have to be direct connect, but we will ask for dual redundant Ethernet connections. These may either be 1 gig or 10 gig connections. As I mentioned earlier on before, the latency must not exceed 150 milliseconds back to the home region. We would expect customers to sign up for enterprise support. So there would be a TAM, of course, that will be at the back end of supporting an Outpost installation. Pricing on Outposts as well is, I'm sure, something that is on everybody's minds this evening. So the way this works is in exactly or in a similar fashion as you would expect to buying an RI. There's a 3-year term or upfront commitment that we'll be looking for. It may be either partial upfront payment, it may be an all upfront payment, or it may be a no upfront option. But these are effectively the payment terms across 3 years that we would be looking for in terms of offering Outposts. This, of course, includes the delivery of the rack, the installation, the servicing of the rack, and of course the removal of the rack at the end of the term. the physical asset does belong to AWS, hence the 3-year term that we allude to. We do have the possibility of upgrading your outpost during the lifetime of the term. This could be within the area of EC2 capacity and, of course, EBS storage. And for EDP customers, there are discounts that we can certainly consider as well. So what does an outpost actually look like from the perspective of the region, or from the perspective rather of the VPC that we will be integrating it with? So here you have the example of a customer who may be making use of a couple of availability zones. Once again, a subnet per availability zone is what this particular topology may look like. Once we pull outposts into the architecture, the outpost would have a subnet of its own. Once again, we never stretch subnets between availability zones, and the same would go for outposts as well. It would have its own inbuilt or in-housed subnet. The outpost would then have the ability to access services like S3 or any other service that we have up in the region, such as DynamoDB and S3, as you see to the bottom of the screen right now, using the concept of interface endpoints, which is effectively private link that we have today within an AWS region. Before I move this, Ahmed, Paul, do we have any questions that you'd like to raise?
Just like he was asking about how updates come from AWS to Outpost. Ahmed would reply that's done from the control.
Absolutely, yeah. That's also quite a popular question, just in terms of how do updates work. This is something that Ahmed Gouda has already answered already. It's done in a very automated fashion in the backend via the AWS control plane. Okay. Another question that I frequently get asked, or we frequently get asked in case it hasn't been asked already, is what happens if Outpost loses connectivity back to the region? So as I mentioned earlier on, the prerequisite is to have dual redundant Ethernet connections that would provide connectivity back to the AWS region. Should both of those connections fail, Outpost will continue to function. What would end up happening is that all of the log data that the various services on Outpost run and generate would all be spooled locally. And once Outpost is able to re-establish connectivity back to the region, all of those logs will be spooled back out, back up into the region once again, as you would expect. So it would continue to run. I thought I had a slide on this, but I think I forgot to put it in. Just in terms of the connectivity as well, important to say at this point, Outpost introduced the concept of a local gateway or an LGW. So the way this works is, as you see in the block diagram to the left, we have a pair of Ethernet switches within the rack. These are called TORs, or top of rack Ethernet switches. Each of those switches allows capability for traffic to break out of the outpost into the customer's local network. So the pair of connections, the 1 gig and 10 gig connections, would actually be satisfied via the LGW construct that you see in the diagram to the left right now. You would also need to configure local virtual interfaces, and those would map the customer VLANs back into the outposts and all of the control plane capability that is contained in there. There's also the capability of LACP, or link aggregation control plane. So these are standard port bundling or bonding capabilities as you have today. So it's either a single 1 gig connection or a bundle of connections that you can use to make up 1 gig or 10 gig. So moving forward, the next announcement that we had, again, at reinvent, was the idea of a local zone. So again, today we have 22 regions that are situated around the world. with 4 that have been announced. There is this new capability of local zone that allows AWS to extend a minimal regional footprint in certain locations. The first of those that will be happening is in Los Angeles. It effectively brings AWS infrastructure to the edge. Again, that includes everything that you would expect from an EC2, a compute and a networking capability. It supports ultra-low latency applications once again. So similar to what the use cases are that would exist in Outposts, but for a lot more hardware infrastructure, this is an area that local zone would satisfy for customers. Very limited availability today, once again, only within Los Angeles. The next capability would be something called AWS Wavelength. This is something specifically that we're doing with telco providers that are in the process of rolling out 5G networks. This really starts to see AWS embed our infrastructure within those telco networks and very, very close to their mobile users. So this gives the ability to the developers or the application developers within those telco customers to start deploying their mobile applications within their 5G networks, and again, very, very close to them, to their customer networks. If you recall, if you've seen some of the speeds that we're speaking about for 5G, this is multiple gigs of bandwidth that can be extended to a single user. So it becomes really important that we're able to provide that bandwidth at a very, very low latency all the way deep into the telco provider. And this is what we aim to achieve today with Wavelength. We're doing that with a few providers. We have them listed here. So today, those would be Verizon, Vodafone, KDDI, and SK Telecom. We expect that this list of telco partners would extend over time. And it is probably one of the more interesting services that I guess I'll be keeping an eye on as we move forward from an AWS service availability perspective. So I'm well within the 1.5 hours time that I've been allocated for the first half of this. If there's any other questions that you'd like to discuss at this time, if not, we can take a break. Ahmed, Samir. Sure. If not, yeah, we'll take a break. The time now is 5 to 7, I guess, in Riyadh. We could probably take, a 15 or 30-minute break. Ahmed, Samir, you want to give us some guidance on that? How long would you like to take a break for? Sure. So we'll take a 30-minute break and we will be back at 7:30 Riyadh time. Okay, thank you very much.